Hello, I'm back. We are going to discuss the estimation method in statistics. So, suppose that we would like to estimate the mean. When we want to estimate, that means we wanted to have the full observation of the population, but that was not possible. So, with the part of the observed sample from the population, we would like to guess what would be the mean if we could calculate from the population. So here, this mean is, so it means that this is the mean that we could calculate if we had the full population. And we are estimating that from the sample, and the estimator is the sample mean, sample average. So you calculate from the sample observations. Then, first, you think about this. It is natural, so estimating the mean by the mean it's natural, but there are theories to justify why it is natural. So first, you think about this. It doesn't need to be actually the mean. So to estimate the mean, you may use any observation, just use any number you observe, or just check the first observation and finish there. Or you may use unequal weights, some kind of more complicated weighted average, or you may alternatively consider median. So when we say y bar is the natural estimator, that means y bar is better than these guys. In what sense? In what sense? That's what I'm going to explain here. How can we argue that y bar is a better estimator than like these kind of estimators? To do that, you have to think about this. We know that an estimator may have random errors. Obviously, random estimation error occurs like almost always. So what we want to do here is we would like to capture the properties, the size of the random error. And to do that, we need to know the sampling distribution. So then we have to understand the concept of the sampling distribution. Sampling distribution of y bar. Y bar is random because, so think about this, y bar is calculated this way. You randomly draw a set of individuals from the population, and that is your random sample. And from there, from those realized outcomes in your sample, you calculate the average y bar. And what's important here is y bar is still random, in the sense that if you resample, if you throw away your sample and retake n number of observations at random, and if you calculate the sample average again, the sample average would be different. So if you regenerate the sample, if you redo the random sampling, then each time y bar, the sample average will be different. So in that sense, we understand that y bar is random. So then, if you repeat random sampling again and again, like you're choosing a person again and again, so it's one experiment. So repeat the experiment again and again, then each time you will have different values of y bar, and if you can do it infinite times, then there will be a distribution. That is the sampling distribution, right? So suppose that n is 100. So you randomly choose 100 people and calculate their average income. That is the first estimator. And throw away these guys and resample another set of 100 individuals and calculate their income, their average income. That is your second estimator. And in that way, you may repeat this estimation infinite number of times, if that was possible. Then your calculated y bar will have different values, and if you draw a graph, you will get a nice sampling distribution, or distribution, which is the sampling distribution. It is the sampling distribution because the randomness is generated from the random sampling. So because whenever you when you repeat the random sampling again, you get the distribution. So because y bar is random and y bar has its own distribution, so you can think about the mean from this distribution. If you can repeat that forever, like infinite number of times, like you calculate the mean from the population, you can calculate the mean of all the infinite number of sample averages. Also variance. So that is, it is purely conceptual, hypothetical experiments, but you have to do it. So because that's how we justify our estimation method, right? That's how we handle the random errors. So this concept, the concept of the sampling distribution, is maybe the most difficult and maybe the most confusing but most important concept in statistics and econometrics at any level. I have seen some statisticians who does not understand this. But it's important. So point is imagining repeating the random sampling. So here is an example. Think about unfair coin. Unfair coin, say 0 is heads and 1 is tails. So, but the coin is unfair. So the probability of head is only 22% and tails is 78%. We call this binary distribution or Bernoulli distribution, but the name is not important at this point. So it's a very weird coin, but remember, if you calculate the mean and the variance, the mean is 78.78 and the variance is 0.1716. I have taught this how we calculate the mean and variance in 320. So you may go back, check the lecture video from 320. But calculating the formula itself, the formulas are not important. So just take the numbers. So by the way, this mean and this variance is when the result when you throw one coin. When you flip one coin, you get this mean and this variance. Now we think about throwing two coins and calculate their average of two coins. So either you have 0 heads, half of the heads, or all tails. So 0 means 2 heads, 1/2 means 1 head, 1 tail, and 1 means 2 tails, right? So we quantified the outcomes in that way. And calculating it is easy to calculate the probabilities because there are only 4 possible cases. It is easy to calculate the probability of each of the 4 outcomes, and then you get these numbers. Graphically, this is the distribution when you throw 2 coins. So the mean is here. Mean is 0.78. But you have probability at 0 and at 0.5 at 1. So 2 heads, 1 head, 1 tail, 2 tails. And still the mean is here. If you throw 5 coins at the same time, then depending on the number of heads and number of tails, you have 0, 0.2, 0.4, 0.6, 0.8, and 1. Still, your view is here. So distribution changes as you increase the number of coins you throw at a time. And what's interesting here is as the number of coins increases, the shape of the distribution looks more smooth and familiar. It is the bell curve. So when you throw 100 coins at the same time, your sample average from those coins will be distributed like this. Compared to the earlier distribution, it's much smoother and much like a nice looking distribution. So then, what we want to know from here? The first, we would like to know the mean of the sample average. Sample average, it is not from a single coin, but it is the average of n number of coins. And then we know that the mean is the same as the mean when we throw one coin. So when we throw one coin, so the mean is the same, and then that means if you'd like to estimate the mean from one coin, then the sample average of n coins is expectedly correct. The sample average, the expectation of the sample average equals to the parameter you want to estimate. You are curious about the true mean, and your y bar is the estimator, and your estimator is correct on average. In that sense, y bar is called unbiased. It is not overestimating, not underestimating. So sometimes it may be larger than the true parameter or smaller than the true parameter, but on average, these errors are cancelled out and on average correct. So it's a kind of another on average sense. And what is the variance of y bar? Variance of y bar is when you throw n number of coins, and then sometimes you may, if you are very fortunate, you will get all heads, or sometimes you may get all tails. However, these kind of events, these kind of outcomes will be very, very rare as n increases. And as n increases, most of the observations will be within reasonably expected range. So the average is 0.78, 78% of coins are expected to have tails. But when you throw 100 coins, it would be somewhere in between, like it will be like around 60% or like 90%, right? It won't be exactly 78%, but it should be somewhere around that. So that means as n increases, the variance changes, the spread changes, the dispersion changes, the distribution becomes more concentrated around the mean, around the center. So the dispersion, the range becomes smaller. So the variance depends on n, especially it decreases, variance decreases as n increases. So we are going to discuss it in more detail later. And also, we will consider what happens when n becomes the infinity. When n converges to the infinity, what would be the behavior of your estimator in the limit? So we will also, I will explain this a little in more detail later. And finally, so we have considered mean and variance, but also we know the shape of the distribution. As I said, the mean is the center and variance is the distance, and still the shape of the distribution is it could be is not explained by the mean and variance, but here as you see, the shape of the distribution will be also very well behaved. It will be the bell curve, the normal distribution that you know. So this is how we justify our estimator, or somehow like when you argue that your estimator is good for the parameter, to estimate the parameter, then those are typical arguments using this example we make. So I'm going to explain them in more detail in the following video.